And I'm Yuki Kaneko from Kyoto Institute of Technology. And today I'd like to talk about fundamental study on full structure interaction models for pulse waveform analysis through blood vessels. And I'd like to start by talking about the purpose and background of our study. Atherosclerosis is one of the risk factors for vascular disease, such as heart disease and cerebral vascular disease. And it is a disease in which atherosclerotic plaques develop on the inner surface of arteries. Symptoms such as thickening of blood vessel walls, decreased elasticity, and the occurrence of stenosis can be observed, potentially causing functional decline or arrest of vital organs. These symptoms often lack noticeable signs, which emphasize the importance of early detection. In addition, atherosclerosis have been observed to form at specific sites on the arterial wall. In this diagram of the arterial tree, the area shaded in black represents the regions where atherosclerosis is most likely to occur. This suggests that the development of atherosclerosis may be related to hemodynamics. In this slide, I'm going to introduce the diagnosing atherosclerosis. Currently, ultrasound examinations are widely used to geometrically diagnose atherosclerosis. However, this diagnostic method requires expensive and large-scale equipment, making them less suitable for the early detection of atherosclerosis. Therefore, more affordable and simple diagnostic methods are needed. Furthermore, it is challenging to assess atherosclerosis from mechanical perspective using ultrasound examinations. Therefore, diagnostic methods focusing on the phenomenon of pulse wave propagation within the body are being explored. Pulse wave propagation is a phenomenon in which oscillation in the arterial wall caused by the blood pulsed by the heart's contraction propagate with blood flow to the periphery of the artery. This velocity is called pulse wave velocity, and when measured in vivo, it is obtained by dividing the distance L between two measure points by the time delay delta t of the waveform. Next, I will explain the methods for evaluating the measured PWV. The evaluation of the measured PWV as a diagnostic indicator for vascular disease is based on the Mons-Korteweg equation. The Mons-Korteweg equation is expressed by the following formula. This equation suggests that changes in the physical property of the vessel wall due to atherosclerosis increase PWV. However, the Mons-Korteweg equation is derived based on idealized assumption and significantly deviates from the geometric and mechanical conditions in actual biological systems. Therefore, diagnosing arterial atherosclerosis using PWV measurements based on PWV-MK could be uncertain. Additionally, PWV has several issues. The PWV obtained by dividing the distance between two measurement points by the time delay represents average velocity between these two measurement points. In other words, PWV is a one-dimensional index and does not consider many other important biological factors. Furthermore, this figure shows a relationship PWV and H. It suggests that there is a correlation between PWV and H, indicating possibility of atherosclerosis progressing with aging. However, the relationship between PWV and H shows considerable variability, and it cannot necessarily be said to be consistently correlated. Therefore, to make PWV a more accurate diagnostic indicator, methods are being explored to extract mechanical information, not only from the pulse wave velocity, but also from the waveform of the pulse wave. Pulse waveform analysis is being noticed as an alternative to PWV testing for diagnosing arterial sclerosis. It is a research area focusing on the wave properties that separate transmitted and reflected waves at mechanical or geometric discontinuities. In previous studies on pulse waveform analysis, Parker and Jones proposed a method to separate the pulse waveform into transmitted and reflected waves and analyze the wave intensity representing flux of energy carried by the waves. Additionally, Fukui et al. Suggests that reflected waves from the stenosis and the annulus have different phases, and the geometric properties of the region affect the reflected waves. The goal of my research is to perform full structure interaction analysis to investigate the pulse wave propagation phenomena and to obtain a more accurate diagnostic indicator for atherosclerosis by unlabeling the pulse waveforms. As foundational research for this, we conducted the validation of the simulation model using PWV as an evaluation indicator, verified computational accuracy with PWV, investigated the effect of mechanical properties of the arterial wall on pulse waveforms, and explored the impact of different inflow velocity frequencies on pulse waveforms. Now, I will explain about analysis methods. The full structure interaction analysis used in this study refers to methods for examining the mutual effects between fluids and structures. Through full structure interaction analysis, it is possible to analyze the effects of blood flow on the blood vessel walls, as well as the influence of the resulting deformation of the vessel wall on the blood flow. For the analysis solver, I use a nonlinear structure analysis solver, Radios, version 2022.3 by Altair. Additionally, ALE is a method that uses fluid computational grids, conforming to solid boundaries, which is particularly effective in full structure interaction analysis for solving moving boundary problems. The simulation model used in this study is a three-dimensional straight cylindrical tube model of the aorta, as shown in this figure. For this 3D model, a mesh of first-order hexahedral elements was created using radios. Then, the governing equation for the fluid is a Navier-Stokes equation and the equation of continuity, assuming it as a hydrodynamic viscous fluid. Also, the governing equation for the structure is the equation of equilibrium, assuming it as a linearly elastic solid. In this slide, I will discuss efficiency of parallel computation. The specification of the PC used in the studies are as shown this. The figure on the left shows the number of threads on the horizontal axis and the speed-up ratio on the vertical axis. From this figure, in 1 to 8 parallel threads, as the number of threads increased, the speed-up ratio increased linearly. Additionally, in 60 and 32 parallel threads, the rate of increase in the speed-up ratio became lower. The figure on the right shows the clock frequency relative to the number of threads. From this figure, even as the number of threads increased, the clock frequency remained approximately constant. In this slide, I will explain the methods for measuring pulse wave propagation. So here goes the results and the discussion. First, I presented the simulation conditions. In this study, while the kinematic viscosity and density of blood were set to value close to those in the human body, but the sound speed was set lower than the actual value for computational efficiency and stability. We evaluated how this affects the calculation by using PWV as an evaluation indicator. This corresponds to research objective 1. Additionally, we investigated how changes in the Young's modulus of the arterial wall due to atherosclerosis affects calculation accuracy. using PWV as an evaluation indicator. This corresponds to research objective 2. Furthermore, a single sine wave of inflow velocity was applied to the fluid, as shown in the figure. While the human heart rate is typically around 1 to 2 Hz in this study, the frequency was set higher to minimize the influence of reflected waves. In this slide, I will explain the methods for measuring pulse wave propagation time. The phase velocity methods used in this study is a technique that calculates PWV from the time shift dt when overlapping pulse waves observed at any two measurement points. Then PWV is calculated as shown this. As an example, when determining the PWV at the 500 millimeter point, the pulse waves observed at z equals 550 millimeters are overlapped on those observed z equals 450 millimeters to determine dt. The PWV at z equals 500 millimeters is then calculated by dividing the distance between the 2 points by dt. First, we investigated the effects of blood sound speed on PWV. We measured the PWV at z equals 500 millimeters with the Young's modulus of the arterial wall set to E equals 1 megapascal. In this case, PWV MK equals 10 meters per second. As shown in the figure on the left, regardless of the sound speed, the PWV remains constant. This suggests that sound velocity of blood can be approximated with a low computational cost using C equals 100 meters per second. Next, we investigated the effects of the Young's modulus of the arterial wall on PWV. We measured the PWV at z equals 500 millimeters with the sound speed of blood set to C equals 100 meters per second. As a result, as the Young's modulus increased, the error between PWV measure and PWV MK became larger. This suggests that for accurate calculation for atherosclerosis with E equals 1 megapascal and 2 megapascal, there is room for reconsideration of the simulation models and the methods for calculating PWV. From this slide, I will explain the results of the pulse waveform analysis. We investigated how changes in the Young's modulus of the arterial wall due to atherosclerosis affects pulse waveforms. This corresponds to research objective 3. This is volume pulse waveform at z equals 450 millimeters. We investigated how the pulse waveform changes as it propagates, focusing on the amplitude. These figures show the ratio of the amplitude of the pulse wave observed at each measurement point to the amplitude of the pulse wave observed at z equals 150 millimeters. As a result, with one increase in Young's modulus, the attenuation of the amplitude became more pronounced. Finally, we vary the inflow velocity frequency and investigate its effects on pulse waveforms and PWV. As a result, as the inflow velocity frequency increased, the rate of attenuation became higher. Since the heart rate frequency in the human body is around 1 to 2 Hz. It is necessary to set the computational model at a higher frequency to achieve accurate calculation. And finally, I will conclude my presentation with a conclusion slide. We investigated pulse wave propagation phenomena to develop new diagnostic methods for atherosclerosis. In the validation of the simulation model, we confirmed that lowering the sound speed of the fluid for computational efficiency does not cause issues. Additionally, we found that at higher Young's modulus corresponding to atherosclerosis, the PWV was calculated to be relatively lower than the theoretical value. Furthermore, in the pulse waveform analysis, we confirmed that the higher the Young's modulus of the Bessel wave, the greater the attenuation of the pulse wave. A similar tendency was observed even at higher inflow velocity frequency. In the future, we will explore methods for more accurate calculations and further investigate the relationship between pulse waveforms and Young's modulus. Thank you for listening.